All right, so one thing I want to make sure you are getting straight in your head is when I ask you, knowing the difference between the word simplify and the word solve. And I think a lot of times you guys haven't had that emphasized to you a lot, or you use the real life definition of simplify, because a lot of times the math definition and the real life, to simplify, make my life easier, blah, blah, blah. That's not the case in math. In fact, you were doing fine until I told you to simplify something, right? So simplify means something in math. Anybody know? PEMDAS. Nice. So simplify means PEMDAS. I was actually, believe it or not, taught PEMDAS wrongly by my pre-algebra teacher. She told me to do the parentheses in order from left to right, then exponents, then multiplication, then division, then addition, then subtraction. But that's not true. It's multiplication, division kind of go together, right? This could be, instead of PEMDAS, it could be PEDMAS or whatever. And then addition, subtraction go together. So this could be PEMDASA or PEDMASA. It could be all kinds of different things, but you have to do that. And a lot of people make the mistake in thinking, oh, especially in this chapter, where I'm mixing up simplifying, I'm mixing up factoring, and I'm mixing up solving. Okay? Factoring has 3 purposes. Can anybody tell me when you would factor? No F. I'm glad you said that, but there is no F in PEMDAS for factor. So if I tell you to simplify, there is only one reason why you might factor. So what? Say again?
Pulling out a common term.
If you put, I know, but that's not simple. That's not PEMDAS. So when would pulling out a common term might fit with this? I'll give you something really basic. What if I told you to simplify this? Then by factoring, let me just say, if I factored out a 3, it's going to help me what? Which is division. The only time I'm going to ever factor when the problem says simplify is if it helps me divide. That's one reason you would factor. The second reason you would factor, and this is especially prevalent in Algebra 1 and Algebra 2. That's not what I was going to go with, but yes, solving is the third one. I always say, and we're going to do that in this chapter. So you would factor up, say, a quadratic or a polynomial so that you can set each factor equal to 0 and solve. We'll get to that really soon. And then the last one, which is especially prevalent in Algebra 2 and Algebra 1, you factor because I told you to, which is only so that you would have practice knowing how to possibly divide or maybe possibly how to solve. So those are only 3 reasons. But you do not factor for the sake of simplifying. If I gave you this and you went, oh, look, that simplifies. Like if I gave you this and went, oh, I can take a 3 out. That'd be like me saying, how old are you? And you go, oh, I'm going to factor 5 out. I'm 5 times 3. I mean, why would you do that? Right? It doesn't make life more simple with math. So no factoring when it says simplify unless it helps you to divide. Good. And then when I say solve, yes, very often are we going to factor when we have like x squared or x cubed terms and we have to factor to be able to solve. Y'all with me on that?
Good.
I'm going to really try to emphasize that more and more. I do all the time. And you heard PEMDAS. Did I mention that already in here?
Yes, it was on the video.
Oh, it was in a video? Good. Just the last one you just watched?
Yes.
Awesome. Way to watch that video. Y'all with me? Okay, so make sure you know that. And because this test is going to have directions that say simplify, directions that say factor, directions that say solve. And every year I have people do the wrong thing on wrong questions. And what they do is correct. They're just not following the directions. And I know it's easy to just look at the math problem. In fact, a lot of you are really good at looking at a math problem and going, oh, I recognize that. You're not going to. I can give you a partially simplified problem or a partially factored problem that could go in the solve direction, could go in the simplified direction, or could go in the complete the factoring direction. And you'll have to read the directions to know. And you'll get plenty of practice with it, but just focus on the actual directions you're going to be seeing. All right? All right, so today we're going to talk about two things. And we're going to have to talk quickly because we have got 30 minutes. All right? So here we go. GCF and LCM. Greatest common factor, least common multiple. Let's start with what most people think is the easiest. The greatest common factor, or from here on out, GCF. What am I doing when I ask you for the greatest common factor and I give you multiple terms? Maybe 2, maybe 3, maybe whatever.
The largest number that divides evenly into those numbers.
Okay, and if there were variables, you'd have to consider that as well, right? So if I give you a number like, say, 18x squared y, and maybe something like 24xy w squared, and maybe something like 36x cubed y squared w, and I said, find the greatest common factor, can you eyeball that and see what it would have been? And what would it have been?
6xy.
So a 6 divides evenly, right? And then also, they all share a common single x, and they all share at least one y. I mean, not at least, but they all share one y, but they do not all share a w. Now I want to show you something. Look what would happen if I did the prime factorization of all of these numbers. And do you all remember how to do a prime factorization?
No.
You remember the little factor tree thing? Don't use that.
Really?
Every year I see somebody do a factor tree, they inevitably lose numbers as they're, because they're breaking it up and they've got all kinds of things, and then they go back and they circle everything and they forget one. A much better way to do a factor tree is what I call upside down division. And upside down division, I really started doing that mainly because you know how when you're working on your page, you complete a problem and then you start a new problem, and there's not any room to divide, and you have division, you need something above. And if you, like for instance, if I'm dividing numbers into 36, like 2 into 36 goes 18, and then 2 into 18 goes 9, and then 3 into 9 goes 3. I can do that, but normally I'm starting a problem without any room above. Does that make sense? And on big numbers, I might have a lot of division going up. So what I do is I just do the division going down. So if I want to find the prime factorization, I'm going to pick prime numbers that go into that, prime numbers that go in, prime numbers that go in, and in the end, it's really easy not to lose numbers. So this 36 is really 2 squared times 3 squared, and then of course the x cubed times the y squared times the w.
Interesting.
Are you with me?
Yeah.
And then right here, I could say, all right, 2 goes into 24. And by the way, you're going to be getting some big numbers. I mean, I know a lot of you can look at 24 and say, oh, that's 8 times 3, so 2 cubed times 3. Great. But sometimes the numbers are big, and it might not be as easy to see that 2 cubed times 3 in there. But I'm trying to show you something here. And then finally, so now you just told me a second ago the GCF was 6xy, right? Now I want you to look at this, and I want you to say, okay, of the numbers that are in common, what's the smallest one of each? Like, what's the smallest number of the 2's? What's the smallest number of the 3's?
3.
What's the smallest number of the x's?
X.
Smallest numbers of the y's?
Y.
And I could have circled this one or that one. And then I can't say the smallest number of the w's. Well, I mean, I can. No w's. So when I'm thinking greatest common factor, which most of you already know, if these numbers get really big and you can't just eyeball them, if you do a prime factorization, you can just grab the least of the 2's, the least of the 3's, the least of the x's, the least of the y's, and technically the least of the w's because this had no w's. And then you just take that 2 and the 3 and the x and the y and you put them together. So your GCF is 6xy. Are you with me? greatest common factor. All right, now, let's look at least common multiple. Now, before we get started, what or when would you ever bother using a least common multiple? So instead of greatest common factor, least.
Oh, the denominator, when you're trying to find a common denominator.
You're trying to find a common denominator. Least common multiples are what you're going to use. So I'm going to use the exact same problem. I'm out of space, but you could just draw a new line right here, leave all this up here and say least common multiple if you're taking notes. Yeah, we're going to use this LCM when you're finding a common denominator. Now, most of you are used to finding common denominators, and the problems haven't been that ugly. But again, what if you can't look at it? You can probably look at 18, 24, and 36. Somebody tell me what they would do to find a common denominator if those were your three denominators. What is your normal practice for doing it? You know?
No.
Some of you don't even know what you're doing, but you know how to do it. It's like, I don't know what I'm doing, I just do it. But like, think about it. What would you do if I was asking you to add? Like, tell me physically what you did.
Multiply the biggest number by 2 or something and see if the other numbers go.
So you're basically trying 36, and since they all don't go into 36, then you're going to 72. Do they all go into 72?
Well,
They do, right? So that's normally what I do. I take that biggest number and I see, well, do they all go into 36? No, then I add a 36 essentially to it, make it 72. Do they all go into 72? If it's no, then I add another 36. Do they all go into 108? And I could keep going all day on this, right? But look, now remember, she already just said that it would, or y'all said it would be 72. Now, how about the variables? I mean, what if that had an x squared y on it? So you got to make sure that that had an x squared y, and this had this, and this had, I hope I'm not off the screen there. You're going to want to make sure you have the most number of x's. Is that what you're saying? So if the most number of x's is x cubed, I would have to multiply the bottom and the top by an x. Or if the most was x cubed, I would have to multiply the top and the bottom by x squared to make it match up. Is that what you're saying? And then the most number of y's would be y squared. So this would have to become a y squared and a y squared, and the most number of w's is w squared? Well, think about what you just said. You're taking the most number of x's, y's, and w's to determine that common denominator. Wouldn't that also work if everything was factored like x, y's, and w's? Couldn't you look at this and say, well, what's the most number of 2's that I have? So for the LCM, I could say the most number of 2's is 2 cubed, which means they're all going to have a 2 cubed. What's the most number of 3's?
2.
So 3 squared, I have 2 3's. What's the most number, what are the other numbers? The most of the x's? X cubed, y's, y squared, and w's. And then what do you think 8 times 9 is? And there's that 72. So my advice to you is have a plan when it's not really obvious. Are y'all seeing that? So for greatest common factor, you're basically looking at the prime factorization and picking the least of each power. And remember, if it's not there, then the least of each term, and if it's not there, that would be the least. So you wouldn't even count the one that wasn't in common. And if you're doing the least common multiple, you're going to take the biggest of each power and put those together. So let me throw something at you that's not totally obvious. See what you can do. And then I'll throw you a dirty curveball. Okay. So what about, let's go with, and if those are my two numbers, and I'm guessing off the top of your head, you can't see the common denominator in there, you might start, like, you might go, well, I know there's a 5 out, so I can just pull a 5 out and then see what's left. And I do that as well, sometimes when I'm factoring. But you could do what to figure this out? Especially since I'm about to ask you about the LCM. So I want to find the GCF and the LCM of both. Any ideas? With our newfound methods? So do the prime factorization. So I'm going to say, well, and always, by the way, don't divide that by, 15. Always pick a prime number to divide it in there. So you can divide that by, say, a 5. So 5 goes into 30 6 times with the remainder of 1. Carry the 1, 5 into 15, 3. And then you know that. 7 goes into that. 9 times, and a 3 goes into 9. 3 times, and there it is. 3 squared. 5, 7, and of course x squared and y. And then what goes into that negative 525? And by the way, do I need to be concerned about the negative? Because it is a negative 1 in there, which is a factor.
Yeah.
Well, how many negatives are in there then?
1.
You sure it's not?
Or it could be.
I mean, couldn't I, let's just see, divide negative in there, divide a negative in there.
Oh my god.
Oh man, I can be doing this all day, right? So how many negatives are in there? Well, some odd number, right? Because it ended up being negative. Well, how many negatives are in this one?
9.
Really? What if there's 2?
Oh my god.
Some even number, right? So are there more or less negatives in that? Because if there's 1 negative in that, this might have 2. Are you kind of following me?
Yes.
And if this one has 2, well, this one might have 3. So there really is no way to determine how many negatives are in there, right? So are we going to worry about it at all? No. So, and think about it. If you're finding a common denominator of 2 fractions, does it ever concern you that whether you're adding them or subtracting them?
No.
Well, that's the plus or the minus, right? You don't even pay attention to that. You just find the common denominator, you adjust your numerators, and then you decide what you do. You with me? And if you're factoring something, like you can always factor a negative out, right? I mean, sometimes you do because it's helpful, sometimes you don't, but you always can. So we're not worried about any of that. So right here with that negative, you're going to completely ignore it, and you're just going to go to the 525. So I'm going to go, all right, 5 goes into 525, 105. 5 goes into that, 21. 3 goes into that, 7. So 3 times 5 squared times 7, x, y cubed, w squared. So what is my rule for GCF? So for the greatest common factor that they share, I'm going to take the least of every factor. So the least number of 3's is a 3. The least number of 5's is a 5. The least number of 7's is a 7. And what would you do if one had a factor but the other did not?
You didn't take it.
Then the least would have been none of those, right? So you would not have taken one at all. And then the least number of x's and y's are xy. And then you would just take your time and multiply 3 times 5 is 15 times 7 is what, 105? And usually the GCF's not bad, but the LCM is a little nasty. And not having a calculator on your test, just suck it up. If you don't multiply it out correctly, it'll probably cost you a point, but it's not going to kill you. Now, how do I find the LCM now that I have it like this? Because think about it. What if those were my denominators? I mean, do you really want to go? All right, it's 525. No, it doesn't go to that. 1,050. No, it doesn't go into that. 1,575.
Yes.
Oh, it does. And you got lucky there. What if it could have gone on, right? I remember doing that in like 4th grade or 5th grade or whatever, writing them out, and then you make a little addition error as you keep adding, and then you go forever and you never find it, and it's just discouraging. Whatever. But what can we do now? For LCM is the highest power. So the highest power would be 3 squared and 5 squared and 7, and then x
Squared
y
Squared.
cubed,
Cubed.
and then w
Squared.
squared. And if you look at this and go, but that doesn't have w's. That's true. No w's and two w's. What's the most? W squared. So here that's going to be a little trickier. So you have what? A 9 times a 25 times a 7. So however you want to do that, the 9 times the 7 is 63. You could do 63 times 25. So what's that, 1575? Not too bad. We can do this all day. You think it's any different if I add another term? What if I added this? What if I put I made that the second term, and then just to show you the prime factorization, that's a 2 squared, 3 squared, 7 x w cubed. How does that affect all of this? Now what's my greatest common factor?
It's the same.
Yeah, because all that did was add a 4 and a what? Couple extra w's, and if I'm taking the least of everything, the least number of 2's is no 2's, still have that in common, still have 1 5 and 1 7 in common, right? And then still have 1 x and 1 y.
Wait,
No.
No.
2 doesn't have.
No Y.
Sorry, 1 2. So you end up with 15 times 7 is 105.
No Y.
No y? Oh yeah, no y now.
And then
Okay,
5.
crap. So it changed everything. So I've got what? 1 3. Sorry, I've got no 5's
1 7.
and 1 7.
1 X.
Slow down. I got 1 x. I've got no y's and I've got no w. So 21x. So totally changed what I could factor out of there. And then for LCM, what happens?
You add
Most number of 2's,
4. 2.
most number of 3's,
2.
still 3 squared. Most number of 5's,
5 squared.
still 5 squared. Most number of 7's,
Just 1.
still a 7. Most number of x's
2.
and y's
Cubed.
and w's.
Cubed.
So this changed a little bit. Is that the only factor out front? 9, 25, yeah, so there's my 9, 7, there's my 25. So it would be my, what did I have, 1575? Is that what I had before?
Yeah.
Times a 4. So whatever that is. Maybe? Yes. 6,300? X squared y cubed w cubed. Now guys, don't do this for LCM if you know how to find a common denominator already. I'm prepping you for an entire chapter on polynomials. And with polynomials, we're going to be factoring to solve. So there's going to be a lot of taking out of GCF to make your problem look a little nicer before you get to the hard part of factoring. You're going to be adding terms in a polynomial, and sometimes those terms are fractions. We're headed to rational functions shortly after this. So to do that, you're going to have to be able to find a prime factorization like this and be able to take the greatest amount. But if it's obvious, then don't worry about it. It's just if it's not obvious that I need you to worry. Now, what if I gave you this question? So this would be as dirty as it comes. Got 10 minutes. And hopefully you won't feel like it's that dirty, but it might be. So what if I told you the greatest common factor of 9,240 and another integer is 210 and the least common multiple is that. Determine the other integer.
What's the thing next to 210?
Sorry, it looks like I-13 in here. So basically what I'm telling you is that there are two numbers. The greatest common factor of that number and another integer. So I've got 9240, and then I've got some other number. And I'm telling you the greatest common factor of these two is 210, and the least common multiple of these two is 138,600. Anybody got any ideas?
Do the prime factorization stuff.
So she's saying do the prime factorization, which makes a lot of sense because that's how I found these in the first place. And before I multiplied them out, they were prime factors, right? And those prime factors came from these. So knowing everything's prime factorization would probably be a good idea. And in the interest of time, I am going to go ahead and just write those out. So what if I told you the GCF, or the prime factorization of this is 2, 3, 5, and 7 multiplied together? The prime factorization of this is 2 cubed, 3 squared, 5 squared, 7, and 11. Are you with me? Just take my word for it, but if you did the factor tree, the upside down division, you'd end up with that. And then the prime factorization of this, just so we know what we're working with here, is 2 cubed, 3, 5, 7, and 11. So let's think. If you were told, let's just pretend we know this number. If we knew that number, and I said find the GCF, what would you be doing? To find the GCF, you would be finding the power that showed up the least in those two, right? So when you looked at this one and this one, you found that there was 1 2 in common. Well, this one has 3 2s. So what does that tell you about that?
That one personally, I want to.
It must have been just the one that had 1 2. Now over here, let's look at the 2s. Over here on the least common multiple, it said that the greatest number of 2s was 3. Well, that jives with what I'm doing so far then, right? All right, let's go to the 3s. What did this say? This said that the least number, or what they shared in common, was a 3. Well, this could have been a 3 and a 3, or a 3 and a 3 squared, or a 3 and a 3 cubed, and they still would have had 1 3 in common, right? But what does that say? That the most number of 3s was 2, and if this one only has 1, then this one must have had 2. All right, let's check out 5s. This said that they shared 1 5, right? Which meant this has at least 1 5, but it might have had 2, 3, or 4, or 5, because no matter what it had, if this only has 1, the GCF would be just 5 there. But this says the greatest number of 5s came from, was squared, so that must have been where? Right over here. Now this said, what? They shared 1 7 in common. So I know that this one has at least what? 1 7 in common. So I know that they have at least a 7, but like before, it could have been more, right? But what does this say?
Only 1.
So the least is 7 to the first, the most is 7 to the first. Well, they both must have had just 1 7. And then that says that's all they have in common, right? So I look back up here and I go, well, are there any numbers I haven't talked about? I haven't talked about that 11, so I know this thing doesn't have an 11, right? And if it doesn't have an 11, that would make sense here, because they don't have it in common. But this says that the most number of 11s was 111. So that makes sense that if this one had 1, this would have none, because if I did have an 11 over here, then it would show up on the GCF. Are y'all seeing that? Is it going to be a whole lot different if I start throwing variables in there?
No.
No, because we're looking at the prime factorizations. So you would look at an x or an x squared, the same way you look at a 2 or a 2 squared or whatever. Got track with me? And that's arguably the trickiest thing I could ask you. And that actually is a little math team question that was asked before. Except it did have variables on it. So hypothetically, what if it had what if this had an x squared y z cubed, and this had an x y squared w? Pretend you don't know that yet. Then my GCF would have been an x, right? And a y, and that's it. But my least common multiple would have been an x squared and a y squared
W.
and a w and a z cubed. So not knowing that, see how it's essentially still the same thing? They have one x in common. That has an x squared. So what must have this had? Just an x. Right here, they have one y in common. That had a y. So I know it has at least one y, but it might have more. Yep, sure enough, it did have more. And then it doesn't have any w's in common, but there is one w somewhere. This one doesn't have it, right? It must be here. And this says the most z's they have in common is 3. That makes sense, but there's none in common. And if there's none in common, this does not have a z. And at the end, what do you do with all this?
You multiply it.
You multiply it all together and you'd be in good shape. Y'all with me? Not too bad? All right, again, if you did not watch that video, please do that. There should be a video tomorrow on factoring, and it talks about like factoring differences of squares, factors, perfect square trinomials, and then I'm going to go through some tricks, some never before seen tricks that you haven't seen. Also, it talks about factoring 4-term polynomials. All right, and that you're going to definitely need for Thursday when you roll back in here. No, what am I? Actually, that's not true. I'm jumping ahead. The video you watch on Wednesday will be about those tricks and stuff like that. Tomorrow we're doing some other things. I think tomorrow we're actually going to be factoring just trinomials, random ones. All right.
Any secrets about the PSAT?
The PSAT or the PACT? Y'all are taking the PACT, which doesn't really mean much. It might give you my daughter took it and they said, you're going to test between a 29 and a 31, and she made a 32 on it. With my son, it said, you're going to test between a 29 and a 32, he made a 34 on it. My daughter never took the PSAT because she went to a different school. But a lot of that would have been right if they hadn't studied so much for the actual test, the ACT and the SAT. My kids, I made them take tons of practice tests. They took it a bunch of times. I gave them lessons, got tutors for them to get their scores up, and their scores ended up pretty good. So for you guys, this is if anything, go do the best you can on it. But next year I'll talk to you about the PSAT. The PSAT is the one that determines whether or not you're a national merit semifinalist. And in some schools, that's a huge thing because you might not get into a Vandy with like my son tried to get into Vandy with a 34 ACT and a 4.3 GPA and didn't get in. You know, he was on the track team and broke the school record in the javelin, didn't get in. But there were other people who were national merit finalists who did get in with lesser scores. So some schools really like the fact that you're a semifinalist, and that's the PSAT, which you're going to take in 2 weeks from this Wednesday. But it doesn't count for you guys. So this year's just have fun with it. But your junior year is the one that counts. Yeah. But the PACT that you're taking, I think we're just trying to be fair to the ACT people like we are to the SAT people. But I don't know that it really directly, maybe your name will get sent to a college and go, oh, look at this 10th grade score, it's pretty impressive. So that might help you a little bit, but I don't know that it is as helpful, potentially. Did y'all have siblings that were, was your brother a national merit guy?
I think so.
I think he was.
My brother.
That's right. That's right. And he had a great ACT score, like a 35 or 36 too, I don't know. Your sister might have been. That's true. Where did she end up going? She did go to Vandy? Yeah, it makes a difference. So, sometimes, I mean, they got a lot of smart people applying at a lot of schools, and any little small thing, or if you love Alabama, like I know Alabama historically gives a lot of money for national merit finalists, more so than like an Auburn or other state school. So you would get a little bit more money going there. Y'all be good?
Still going to the video.
Yes.